Hello guys, my name is Vlada, and in this video we will do our very first example of line integral of scalar field, of course. Line integral over curve L of scalar function x times y times line element, where L is given by equations x is equal to cosine t and y is equal to sin t, where t goes from 0 to pi. Okay, this is our problem. Let's get back to the big picture from the previous video. We have to notice first that we have two-dimensional problem. Line is in the real plane in R2, and our scalar field is from R2 to R, so this is a 2D problem. Let's see our steps. First step is to parameterize our curve, but if you watch more carefully, this thing has been already done here. So this is pretty much the parameterization of our curve that has been done. We don't need to do anything in first step. Okay, second step is to calculate line element ds. Second step is to calculate line element. ds is equal to, let's see, square root, this square root, okay, square root of derivative of x squared plus derivative of y squared times dt. Okay, times dt. First, let's calculate these derivatives. Derivative of x is equal to, let's see, derivative of cosine t, and that is equal to minus sin t, and derivative of y is equal to sin t, and that is equal to cosine t. Okay, and let's plug in our result here. Here we have minus sin t squared plus cosine t squared times dt, and we can just ignore this minus here because this expression is squared. So we have sin t squared plus cosine t squared times dt, and using the trigonometric identity, this is equal to 1. So we have square root of 1 times dt, and that is equal to dt. So we have calculated ds, and ds is equal to dt. Okay, let's just frame our calculations, something like this. Okay, and these were our help calculations, finding derivatives of x and y. Okay, That was second step. Let's do the third step. Third step is to plug in our result. Third step is to plug in. Okay, let's plug in everything. Integral over curve L of x. Okay, that is not x. X times y times ds is equal to, let's see, ordinary integral from a to b. Here t goes from 0 to pi, so a is equal to 0 and b is equal to pi. X is equal to cosine t, and y is equal to sin t, and this line element ds is equal to dt. Okay, we have reduced our line integral problem to an ordinary integral that we have to solve. First, we will use trigonometric identity, that this is equal to half of sin 2 times t, and this 1/2 will go out. Okay, and integral from 0 to pi sin 2 times t times dt. Now let's find the primitive function of sin 2 times t in order to use Newton-Leibniz formula. That will be our help calculations. Some primitive function calculations, sorry. Sin 2 times t times dt is equal, primitive function of sin 2 times t is equal to, let's do substitution, 2t is equal to s, and let's differentiate these expressions. d2 times t is equal to ds. Okay, let's remind for a minute ourselves that dft is equal to derivative of f times dt. So this is equal to derivative of 2t times dt, and that is equal to 2 times dt, and that is equal to ds, which means that half of ds is equal to dt. Okay, let's substitute that. Here we have sin s times ds, half of ds, and this 1/2 goes out. We have sin s times ds, and this is elementary integral minus cosine s. Okay, let's just get back our substitution. We have minus 1/2 of cosine 2 times t. I didn't write plus constant plus c because I don't need that here. I only need one primitive function. That is enough. I don't need plus c. So let's get back here. 1/2 times 1/2 times minus 1/2 times cosine 2t from 0 to pi. that is equal to -1/4 cosine 2t from 0 to pi, and that is equal to -1/4. Let's just plug in pi, cosine 2 pi minus cosine 2 times 0, 0. This is equal to 1, and this is equal to 1, so our solution, our result here is equal to 0. Okay, third step, let's frame this third step thing. Okay, nice. And that is pretty much all from this video. See ya in next video. We will do a slightly harder problem where we don't have this parametrization. We have to do the parametrization of curve. So see ya in next video. Bye bye.